it again. So we've got a tank circuit sloshing backwards and forth. But remember before, that one was SL, this one was 1 upon SC. Now let's try and do this in this parallel configuration and replace those values in there. So what have I got? I've got SL times 1 upon SC all over 1 upon SC, well I don't know which way round it is, but 1 upon SC plus SL. Can you see that? Yeah. So what can I do to that to make that better? Well, I mean that's all in the multiply position, so I can bring that to the bottom, right? So that becomes 1, and that becomes S squared CL, and that just becomes SL. So the final thing is SL upon S squared CL. Well, how does that help you do anything? Well, now what I can do is, of course, I know the equation for a potential divider, because that's what that is, right? So this has now become that. So I can just plug that into R2 upon R1 plus R2. So it's V out equals V in. And I'm not going to go any further, but you would just plug that in to the position here where this is regarded as R1 and this is regarded as R2. But we're using algebra. And algebra, you can go back and check your mistakes and eventually you'll find them until you get the right answer. Now, isn't that marvellous? Because if I can express the parallel configuration, doesn't matter how many are in parallel, I can still express it. I can express the serial configuration. I can express the potential divider configuration. There's nothing left. Except this is a parallel configuration, which is a band pass. There's another one that looks like this, which is quite similar. Doesn't matter which way round, the inductor and capacitor are, by the way. And that's a band rocker. So you could do the maths of that, and quite clearly that's just R1 plus R2 plus R3, and you would put those together, tidy them up, and you get a different expression. You don't need to put it into a potential divider equation anymore because there is no potential divider. There's lots of different configs you can have for that as well. So another config would be, which is more normal to do it this way. That's still a series circuit because it's got a path from the high down to the ground. So that's series as well, that's parallel. The magic of filters. And you can just carry on in complexity. You can have circuits, obviously, that, let's say I stuck another one here. Well, all I've got is what I had originally, so I've got this in parallel that I've calculated. I've got this as part of a potential divider that I've calculated. And then all I've got to do is add SL on the end there, and I've got that component in there as well. So I've got a mathematical expression for everything. When I get the final expression, all I do is look at what S is, 2 pi f, and I say, okay, I'll make it really, really big. What happens to the output? I'll make it really, really small. What happens to the output? But with these kind of circuits, they do something in between the really big and the really small. That's where you've got to be careful. And that's why you start to try values in the middle, or you use a simulator. And that's the other possibility here. So where are we for time? We could do a really, really quick simulation just to bring people's memories back. Let's model the parallel case there with R1, C and SL. Let's just give that a quick go. So I'm really, really going to go fast on this because you know how to draw these things down. So I'm going to do place, components, what do I want? I want a resistor, don't I? So sources, no. Basic resistor, place a basic resistor, okay. Next one I want is a capacitor, place a capacitor. Down it goes, and the next one I want is an inductor. place an inductor. I'm going to use the default values. A millihenry is quite a big inductor. 1 microfarad is a moderate size capacitor. And I'm going to clonk OK. So now I'm going to wire the circuit up so it looks a bit like it did on the board there. Rotate that. Down to there somewhere. Okay, looking good. Bring that across to there. Now remember also what I had before is I want to place a connector. Not the through-hole connector, this is just a higher up connector. This is for the simulator, remember. A different type of connector if you remember to last week. So we've got that, we've got IO1, we'll place another one. Higher up connector. I'll do that too. Rotate that. And I'll rotate it again. What have I done wrong? Nothing. Right, so now let's wire them up. Oh, we've got to place a component, and that's going to be. Let's get my light. I'm getting tired. Sources, and finally, it's a ground, isn't it? It's down here somewhere. There we are. There's the ground. And plonk that there. In actual fact, I don't want that IO there. I'm going to delete that because I'm going to put a signal generator there. So I'm going to replace components. Signal sources and that AC voltage, we're going to put that in there like we did last week, and we're going to wire it up now. So, wire to there, wire to there, wire to there. So far so good. How best to do this now. So, let's go to there. That's wired. That's wired. And that's wired. Okay, so hopefully that bears some resemblance to the one on the board. It doesn't matter what frequency you put in because I'm going to do an AC analysis. In other words, I was saying to you earlier that you can have a very big signal, a very small signal, or a signal somewhere in the middle. We can do better than that. We can scan all frequencies using the simulator. So let's give that a go. So simulate analyses and simulation here. And we want to do an AC sweep. We need to set our outputs. Well, I've forgotten myself, but it's IO2, isn't it? So IO2, we add that onto there. We need to look at the frequency parameters, so we're going to go from 1 Hz to 10 gigahertz. That seems quite high to me, but we'll run anyway. And we run it, and look what I've got on there. I've got a bandpass filter. Look at that. Go and have a closer look if you don't believe me. You can plot it in log form, it's a lot more pronounced. But what I said with the maths is right? So we just showed the numbers work, we just showed Laplace works, and now we just did a simulation and we got exactly the same thing. So that's like a tuner on a radio dial, and if I modify, and I invite you to do this, if I modify the size of the inductor capacitor, if I modify the size of the resistor, it will just attenuate it. That's all that's going to happen with the resistor. But if I modify the L or the C, I'm going to shift one way or shift the other way, which is exactly the same as this. So here I'm modifying the capacitor, because I've got a tuning one. If I modify the value of the capacitor, I can modify the point at which it lets through. I've got a radio tune. Magic, yeah? You see why I like electronics? It just all fits together. There's no gaps in between. It's just, and eventually you kind of get this bigger knowledge that just allows you to work things out. Even if you don't know what to expect, you can think about it for 5 minutes and then make a prediction. And then when you actually do it and your prediction doesn't come true, chances are you made a mistake in what you're trying to do and that your prediction is actually right. And that's kind of what engineering's all about. Trial and error to an extent, but also trial and error offset against what you would expect to happen in an ideal world. Okay? Okay, I'll draw this to a close now. Have we got any questions? Are you having fun? Sort of. Sort of. Well, I've said to you before, to actually pass this module is a walk in the park. You've just got to do those two deliverables. But what you kind of pick up along the way is a lot more exciting. And it's the sort of thing that an employer will ask you as well. They're not going to say what, you know, they are going to say what simulators you use and everything. But on those type of questions that they ask at the board, as it were, they're going to say, right, you've got a resistor or a capacitor, what happens if I join these together? A completely open-ended question. Well, what does happen if you join a resistor and a capacitor together? The stock answer I would give is nothing. It's ain't got a power supply. Shows that I understand the scenario, right? But that's how they discern between someone that knows something and someone that doesn't know something, is they just ask the most basic question that you could possibly imagine. If you don't know what an inductor or a capacitor does in conjunction with other components, you're going to get caught out on it. Okay? Splendid. Have yourself a nice lunchtime, and I shall see you next time.